Okay, good morning everyone. After a brief war, we are back. Hopefully peaceful to the end of the semester. So today I'm going to discuss dynamical solutions of the Maxwell equation. So we are interested in the electromagnetic field generated from moving charges in general. And let me give you some flavor of the kind of problems we will be interested if we have enough time today, and if not, next time. So let me ask you the following question. Let's say I have some coordinate system x, y, and z, and let's say I have a particle who's moving with, let's say, with a constant velocity v in the x direction. Also, let's assume that this particle is a point particle with charge q. So it's moving like that. If it would be at rest, everything would be simple. Why would it be simple? I can ask, what is the electric field, for example, and if it's at rest, what is the answer? It's simply the Coulomb law. Very simple. But now it's moving. Now, there are two ways to look at it. One of them that we'll do with today, and the other one that we will do hopefully next lessons. One of them is, let's go to the frame where this velocity is 0. Let's go to a moving frame. This is related to chapter 11, I think, no, 12, to Lorentz transformations, and this will be done later. But let us work in the laboratory reference frame where this is moving. And then we ask, what is the field that it generates? So maybe intuitively, maybe yes and maybe no. So first of all, what is generated, first of all? Is it only an electric field? Like if it was on rest, it would be only the electric field, right? And now, because it's moving, it is creating some current, right? And this current is also creating a magnetic field. So first of all, we'll have both electric field and magnetic field, unlike the case where he's just sitting and not moving. And the electric field and the magnetic field has to be related one to another because of the Maxwell equations. This is obvious. Now, the question is, I'm at some time t. So t is going to be called the laboratory time. It's always called the laboratory time. But actually, in the problems today, there will be another time, actually two more times. What are these times? One of them is going to call the retarded time, and one of them is called the advanced time. The advanced time is not physical, so there are going to be essentially two times. One is the retarded time, and the local time, the time that we are talking now at some given time t. Roughly speaking, what is this retarded time? The retarded time is some previous time that I'll define later, where we are looking at we have some observer also, let's say here. So we are asking, what are the fields, electromagnetic fields at this point? And then the question is, we are now at this point. This is time t. Does the observer here know that you are here? Can he tell? Can he know for sure that you are at this position? Okay, you can say, he can look. But if you think about it a little bit physically, there's no way that you know at time t, I'm looking here at time t, that you are here at the time t. The reason is that the information of the charged particle that is creating the field here cannot go from here to here at infinite speed. It has to go in finite speed. So, for example, if I had here a velocity v, and then I suddenly, just the epsilon before time t, I suddenly moved up or accelerated, will he know about this? The answer is no. And this means that this observer, what does he care about? He cares about time t. Time t is going to be important, but he really cares about also the previous history. So along this path, there is some point in space here, where if you emit a light, tuck, 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 it will reach the other point, the observer's point, exactly at the moment t that we are looking at. It's very simple. If there are stars in the heaven, you know that they are not emitting right now. They are emitting even the sun 8 minutes ago, and it takes some time for the light to arrive. So the relevant picture that you perceive is the history. Now, what does it mean? It means that when we will calculate the fields here, E and B, or more correctly, the potentials here, these will depend on the history, on not on the where you are right now, but where you were in the past. And this is related to retarded time, to a previous time that we need to define, and there is also a previous position. This specific position, we need to understand what is it, how do you calculate it. This has many, many different consequences. So, for example, imagine two particles, two different systems, both of them with charge q, both of them in the x direction, but one of them I start the motion at time t equals 0. So, particle 1, model 1, for example, I have x versus t. This is x equals 0, but it was standing. So I have a particle, I put it in, it's not moving, and at time t it starts moving. Time t equals 0, it starts moving like that. And model 2, for example, it's the same speed, it's just moving forever. Started from minus infinity, it's moving like this. These trajectories from time t equals 0 forward are exactly the same. But will their electric and magnetic field be the same? The answer is no. This motion that you had in previous history may influence you and may not, depending how far you are, etc., etc., all kinds of things. It's rather complicated. But this implies that if I know, okay, I have a particle time starting at v, and I measure the electromagnetic fields, and in principle I can distinguish between these motions. Some information is coming from the past, and you can distinguish in principle by measuring locally at time t, not looking at the past, but looking at time t, what are these fields? Maybe somewhat similar to that we look at the sky and then we see backward in time, what happened a long time ago, Big Bang and things like that far away. Similarly here you can see this now, but now with electromagnetic fields, this will be present. For example, let us look at this model where you stayed at rest and then you started to move, and let us say we are now at some time t here. So this particle was at rest for a very long time, and then it started to move later on at time t equals 0. But let us look at a circle whose distance is ct. What will be what will be E here in this case? So this is ct. So what does it mean this is ct? This is the radius. No information can go beyond this radius, right? The observer here doesn't know that this guy started to move at time t equals 0. No information. So what is the E and what is the B here?
0.
B is 0, and E is Coulomb's law. Because he was at rest.
Because he was at rest, so yeah.
Forever.
Forever.
Assuming the charge wasn't created at some time t. So here, this is just going to be the Coulomb law. In this case, and there is some kind of barrier in space, where after which, it's very simple. You are just Coulomb. What happens exactly on the border is actually very complicated, because you see there is a discontinuity here, This creates a mess on the border, on CT. And in between you'll have, you'll have a time dependent, and in here you'll have a magnetic field and an electric field. And you'll have flux of energy coming out. You'll have a pointing vector that we discussed going out here. And this is very different than the other problem where E and B are going to be everywhere something. There's no such thing as B equals 0 in this problem. Okay, and then when we ask these type of questions, let's say with this case, we look at time t, we ask questions like, these are very subtle questions. So the particle is moving like this, and you are now, your observer, let's say, is in front of him. Or maybe the observer is in this, behind him. Or it can be on top, or it can be on bottom. The question is, will the electric field, for example, be the same up here and down here? Well, from symmetry it looks like it because the particle is coming from here. But will it be the same here and here? It's not an obvious question. And these are the type of questions we are interested in, and that is, so what will happen as the bottom line? Let's say this is distance A, then I can go, for example, backwards in space now, distance A, or I can go upwards, distance A, or I could go downwards, distance A, right? I can also go outside of the board, but it's the same as going inside the board because of symmetry. In all these directions, let's say the electric field, what will happen? Well, up here and down here, you can say from symmetry they'll be the same magnitude. We need to think about what is the thing. But is it going to be here stronger compared to here stronger compared to there, or vice versa? You will see this is, in my opinion, highly non-trivial, because there are several effects playing together in these type of problems. It's not a simple problem. It's not, I here emphasize the retardation time. That's one effect that we're going to discuss today. But there are other effects related to actually something called Doppler effect and to squeezing of space itself. So all these questions, these are highly non-trivial. And then as usual, I encourage you to read in Griffiths. And what I'll do today, there's a huge amount of math. I will not derive all the math that is in Griffiths, but I will derive some of the math, which is not in Griffiths. At least at one point I'll do that, but at other points I'm not going to go into the details, because it's really very much involved. But if you have time, I encourage you to read this chapter more and more and think of what's going on, because this is essentially what Einstein did when he finished his undergraduate. He went to work in a kind of office of patents, and then he read electrodynamics, and he understood this, and from here came all the relativity, not from mechanics. So, and again, relativity and Lorentz transformation we will discuss later. Okay.
What chapter is it?
I'm now at chapter 10.
10.
Yeah. So chapter 9 is all kinds of applications that were discussed mainly by the teaching assistants. Chapter 8 was the Maxwell tensor, and we'll hopefully go next week to chapter 11, which is radiation, which is related to this thing. So there is another physics here, that once you have a particle, especially if it's accelerating, it's also going to emit radiation. So it's involved. That's chapter 11. And that's radiation. Okay, so the first thing we want to do is to introduce potentials. And there are two types of potentials. So first of all, when we studied the statics, we have two types of potentials. We call them capital A, for vector potential for the magnetic field, and we have the potential V for the electric field. And what we did was we lived in separate worlds. we solve this problem by itself, the electric problem, electrostatics and magnetostatics. This doesn't happen anymore, and this is essentially, for example, because of Faraday's law that connects the E and the B, and also Ampere's law, which connects E and B. So you cannot do this anymore when you deal with the dynamics. What do I mean by dynamics? We are looking at fields now, E and B, that depend on time. What does it mean that they depend on, why do they depend on time? Because the density, the charge density rho, and the current density J, in principle now depend on time. So the general problem is give me the density of charges, give me the current, which change in time, find the electromagnetic field. So we will be able to write some formula as an integral, as usual, but this integral is, it was also bad, I think, in electrostatics, but this integral in most cases is very difficult to solve. Then we need to go to specific problems where we can solve these integrals and see what is the physics out of here. So let us look at these equations. So first let's look at Maxwell's equation. We are solving Maxwell's equation. So as usual we have div E, this you know already, and this I'm going to call Gauss law. Then I have div B equals 0, that is n for no charges or no name, whatever you want. Then we have rotor E minus dB dt. This is of course Faraday. And then we have rotor B equal U0J, which would be Biot-Savart essentially,
Minus.
plus U0 epsilon 0, and this is the correction due to Maxwell, but I'll still call it Ampere because I call all together, we call them Maxwell. So these are the four equations. Now, first I can remark something a bit strange. If you go back to the two examples I gave you here, you see I have here time derivatives of E and B. So it looks like, right, think about it. Now think about this particle that was standing and then moving. So, okay, so before that, here I have rho and here I have J. So in principle, in general, I have some rho. Later it will be called R prime and T. And inside here I have J R prime T. These are the current densities and the density of the charges themselves that are complicated function of space and time. And then we want to use them and find E and B, and because these depend on time, also E and B will depend on time. This is obvious. And what will be, so I mentioned before, the simplest case of a charge, of a single particle, which is a point particle that is moving. So what will be, in this case, rho, for example?
Would be Q, the charge of the
Q
particle.
times something, I mean, it's a charge, times a delta function.
Yeah.
So, okay, later we will replace this by delta function when we want to work with this point charge. But in general, generally we can have a plane, we can have a wire, we can have many, many different things as usual. But if you look at these equations, you see here there is a time derivative, here there's a time derivative. It looks like they are defined from time 0 forward, right? So give me the initial condition and move forward in time. This is usually how you solve these type of equations, right? But I said it depends on the history when you have these two particles. One is moving and one is like that, right? So how come you really care about the long history when you have a local in time here and the initial condition here? The answer is that in these two problems, when you think about it, one is moving forever and one is starting its motion, the initial electric field at time t equals 0, and the initial magnetic field at time equals 0, and these two problems are different. Because in this case, you start with B equals 0, and E, just the Coulomb law. And in this case, because you were moving, the starting point is different. So you need to calculate what happens in the past in order to start these equations to progress them in time. And in these two problems, the initial condition will be different. So this is a conceptual issue that the history is present even though these are local in time equations. They do not, you don't have here some kind of integral that goes backward in time, some convolution going backward in time. It's local, but in these two problems, the initial conditions will be, for E and B are not the same. Now, this is not how we solve it. We solve it actually with boundary conditions. We solve it with boundary conditions in these two kind of problems. And in this way, the local in time aspect is present, but unlike Newton's equation, where in Newton's equation, if you have the velocity of the particle and you have the position of the particle at some time t, then you know the future immediately. Here it's a bit more subtle because of these things. You create a field, because here we have fields, not like Newton where we have a trajectory, and the field at time t equals 0 depends on your history, and then when you propagate it, the whole history becomes important. From here, roughly speaking, comes very novel effects and highly non-trivial effects. So we want to introduce potentials. So we have two potentials. One of them is A, R and T, and another one is going to be V, R and T. So these are certainly related to what you already know, and the new thing is that we have their time t here. So there will be another coordinate inside these potentials. But also we need to change a bit the definitions, operational definitions of these two functions. It's not the same like in statics. And now I'm going to explain this. So first of all, this A and this V, what do they give you essentially? They give you E and they give you B. But how do they give you E and B? So we know in statics how this goes. So first of all, B, I claim, is still rotor A. And this is exactly like what you know in statics. And the reason for this is what? What equation tells me that this is correct? This one. So from N, I know that this is still valid, and the only change here is now that the A depends on time, and B also in principle depends on time. But what happens now? What happens with the second equation? So for that we want to use. Let us use Faraday. So I can write rotor E equal minus its dB ddt rotor A, because this is just the magnetic field. So I can write rotor E plus ddt A equals 0. Now, I know that this guy, rotor of some function of x and time and space, is 0. What does this mean? That there is a scalar field V, that all this object is simply dV, because rotor of dV is equal 0. And this is, again, you know this already. And previously, this was only when this guy was not present, right? When you had statics, then you had rotor E, and then you could define the potential as usual, which is div V. Now all this thing is going to be called div V. Just that's the modification. So what we have here is the following. We're going to say E is div V, like in statics, minus ddt A, or is it plus? Yeah, this is correct. So you see immediately here, then if I just plug this definition inside here, then this guy and this guy will cancel, right? And then I'll have rotor of div v, and that is equal 0 as usual. So what is new here? It's a pain. You should hate it. Why should you hate it? Because up till now, what did you do? You wanted to calculate the electric field. What you did, you solved Laplace equation, which is not easy, but in principle. And then you calculate the div v, and then for E it was easy because you didn't have this term. And then you had a separate problem for A, and you calculated B. But now this is not true anymore. What does it mean? If I want to calculate the electric field, I need to calculate both V and A. So there's double the amount of work. And after I calculate V and A, then I can find E. If I just calculate V by itself, it's not good enough. That is the price when it depends on time. And you see that this is a time derivative. So for a static problem where A is independent of time, this is simply 0. And we go back to the well-known definition of the potential. So here we are done. So what is the goal now? We want to find equations. We want to find equations for A and V. The philosophy is simple, and it's like what we had before. The philosophy is that we hope that the equations for A and V are simpler than the equations for E. And we have some knowledge about electrostatics, and we know that this is reasonable in electrostatics, and we will see that it is also true here. And later when we always, nearly always, derive these vector potentials, E, A, and V, and then later use this equation and this equation to find the B, and instead of solving directly the Maxwell equation. You can do also in the other approach, but it is more, generally speaking, more complicated. Okay, so now what we used so far, we used these two equations. So now what we need to do is let us try and play with G and A in order to find the equations that we are looking at. So let us look, for example, on div E equal rho epsilon 0. This equation. Then we can say, okay, let's plug in the definition of, so what will we get? So div E, I apply it here, so what will I get here? I'll get the Laplacian, like in statics. And here I'll get minus d dt div A equal rho over epsilon 0. This is the equation for V and A. I mean, one of the equations, because we didn't use so far, we didn't use this one. I'll have another equation soon. So when you look at this equation, what do we see? If this doesn't exist, we see Poisson.
And in Coulomb-Gauge, it doesn't exist.
Okay, and that's a good suggestion for beginners, but we will see that it's not a good suggestion for non-beginners. So, as mentioned here, in the Coulomb-Gauge that we already discussed, div A equals 0. This makes me very happy if I look at this equation, because then what do I have? I have Poisson equation. The difference is now that this rho depends on time, this V depends on time, okay, but it's the same Poisson equation. But this will create problems when we create A, and we are going to delete this Coulomb-Gauge and replace it by a different gauge called Lorentz gauge, which is used in these dynamical problems. And this is my goal now is to explain what is this Lorentz gauge and why Lorentz gauge is preferable to the Coulomb. Even though if you just want V, then yeah, maybe use the Coulomb gauge, but remember, you will pay the price because you need A, and the equation in this gauge for A will be terribly complicated. So it's not a good approach. We're going to forget about Coulomb and we go to Lorentz. Lorentz is, of course, from the Lorentz transformation, and we are seeing that, okay, relativity is entering. You see here that U0 epsilon 0 is 1 over the square of the speed of light. So obviously they have some connections. And also what we are looking for, we want to have some symmetrization between space and time. Why do I say this? Because in special relativity we understand there must be some connections. That is, the space-time is like a four-dimensional space. So we are looking for this, and soon we will find it. But if I take this to be 0, like you suggest, it doesn't show up, right? Because here I have just space, and then you take out the time, and also here you have a mixture, and the mixture is not symmetric. Time and space are clearly not symmetric here. So we want these equations where time, and this will become clear soon, where in some sense time and space are treated on the same level. Of course, they don't have the same units. When I say time and space, I mean, let's say x, y, z, and what is the time? Ct. These are the 4 vectors that somehow has to show up here, and will show up in the Lorentz Lorentz gauge. Okay, so let us wait here. I didn't choose a gauge yet. So let us now look at this equation, ampere, and let us see where the math leads us to, at least. So what do we have here? We have rotor B, but B is this guy. So we have this rotor A, and this appeared already several times, if you remember or not, but this can be divided into two terms. Someone remembers, or you don't remember?
The divergence of the
yeah, and what?
The Laplacian and
the Laplacian and the divergence, exactly. So the Laplacian already makes me happy because we have already one Laplacian. We like Laplacians in principle. So, okay, so this is the B, and then, where am I? Yeah, here. This is equal U0J. So J and rho play the same kind of role. These are sources that create the solution. And then I have this thing here where I use this definition. So I have the minus, you see the minus from here. So I have U0 epsilon 0, that comes from here. And then I have div d dt v minus U0 epsilon 0. Here I have ddt, and here I have ddt. I'm so happy to see second derivative. Not really, but second derivative of A. And this second derivative is what I called before the symmetrization, where you have something like the Laplacian, and you have, which is the second derivative with respect to x, y, and z. And here I see the second derivative with respect to t. And it also reminds you of something else, maybe, which is the wave equation, where you have all these second derivatives in space. So now we can write this simplification. We're going to do this as, okay, let us write it here. This is the Laplacian with a minus sign, sorry, with del div A. So this is a scalar, and then eventually all this guy is a vector. So what I'm going to do is I'm going to tidy this. You see, like you have here, the sources on the other side of the equation. So I'm going to bring this to the other side of the equation with a minus U0J. This is equal to Laplacian minus U0 epsilon 0 second derivative of time A. So I treated this guy and this guy, and now I'm left with minus U0 epsilon 0 ddt v, all the junk, this one. Maybe I'll, yeah, okay, let me write it like this. Minus, I'll take out, you see here I have this del operator, And also here I have the del operator, so I'm going to write it as the following: div A, which is this one, plus u0 epsilon 0 ddt v, which is this one. See the minus, and I think I didn't make a mistake. Now, let us look at this equation. So this is the source, the current. This one I called a nice one. This is the wave equation. And this I call the ugly one. So the Lorentz goes, I'll soon prove the Lorentz goes a little bit. I'll discuss it. The Lorentz goes says we are allowed, I'm not proving this at this moment, this guy is going to be equal 0. Let us assume that I can do this for now, and let us see what is the consequence. So this is the Lorentz goes. Lorentz, I never remember it with a T or with there are two Lorentz.
You have to find an A and V which set this.
I can. Okay, so let me explain what I mean here. That I can take them to 0. I can always find an A and V that has this condition. We can start with some A prime and V prime which do not satisfy this, then perform a transformation. I'll soon discuss this. And then the pairs of A and V and the new A prime and V prime have the same electric field and the same magnetic field. You know this already from the static case. For example, this you know it from high school for the potential. The potential you can always add a constant because when I take the derivative I get 0. So the gauge there was plus a constant that you didn't care about. Here it's more complicated. It's plus a function that depends on time and space, and you can have freedom. Now, if you want, if you don't like Lorentz, you can invade. What is your name? I forgot. Offic. You can make the Offic gauge. No one will pay attention to your gauge, but you can define a gauge as you wish. Now, sometimes there are clever gauges beyond Lorentz and Coulomb. Coulomb and Lorentz are the most famous ones, but I'm not claiming they are the only ones. We can create an Offic gauge, and then this is, let's say, not 0, and you can solve this in your gauge. But the fields, what is important is not A and V. Eventually, what is important is E and B. That's the physical reality. So there are many infinite amount of gauges, right? And this is the idea, and the claim, I didn't prove it yet, that we can choose this one to be 0. And why is this useful? Because then I get to see an elegant equation here. You see, this is gone. I mean, this is very nice. That's the idea.
No.
But you pay a price here, you think. But let us see what price you pay in the other equation. But the price in the other equation is going to be actually making it even nicer, not worse. At first you say, the reason is what is this object here, div A?
It's minus u0 epsilon 0.
So, okay, so maybe you don't like this, let me go back, but div A in the Lorentz.
Can you just ask?
One second, let me finish. I'm so excited. Minus u0 epsilon 0 ddt v. So when I'll plug it in, let's call this guy I plug it in, then I'll have here the second derivative, and then I'll have here a plus, and the second derivative with respect to time. I hope you all see it. And then what we get is minus. Okay, and now I'll do another thing, because here I have a minus. I'm going to take the minus and put it on the other side. So then I get the v u0 epsilon 0 second derivative with respect to time of v. Again, here I have the derivative of time. I put it in, second derivative. This is equal rho over epsilon. And now even though we didn't solve anything yet, from an aesthetic point of view, this is nice, because you see this equation where this is 0 for A, and this equation for V are actually have the same structure, because both of them have the Laplacian, the second derivative with respect to time, here of a scalar, and here of A. And when you think about it, what it means that the vector A has three components: Ax, Ay, Az. And now, like you have x, y, z, and Ct, and now we have Ax, Ay, Az, and the potential V. They all come together. It's like a four-dimensional object. And the equations that we have here, of course, here you have a source, which is a vector. Here you have a source, which is a scalar. But again, this is only one component, and so you can think about this as three equations. So to summarize this, we get now the following equations. These are the basic equations, together with this one and this one. They are different, from which we get the fields. And of course, they are all based on Maxwell's equation. So what are the equations that we received? So let us summarize this briefly. Summary. In Lorentz-Gauss, we have this square times A equal U0 J, and we have this square times V equal minus rho over epsilon 0. And what is this square? This square has a name. So it was, this part is called Laplacian, so there's a different French guy for this one. It's called D'Alembertian. It's not guy from the Musketeers, there's some French guy, D'Alembertian. And this is simply the Laplacian minus U0 epsilon 0 second derivative of time. So this is a definition. These are the equations. You see that in this D'Alembertian, space and time are treated not exactly the same because of the minus here. Again, this U0 epsilon 0 is 1 over the speed of light, so squared. So this is 1 over c squared. So you see everything is treated in a symmetric way, and these are the basic equations. Yeah, what is the question?
Here, you should have constraints on A and B from setting this down to 0.
Right. The constraints are that this is 0. So the constraint is this one. And this constraint is important. For example, if you solve equations and you are using these equations, you work hard and you find, for a simple problem, let's say you are able to find a solution, you should check that this is correct. If it's not correct, it means that you made a mistake on the way. But this is the constraint. So, and this is a good way to find mistakes in exams, for example, if you have time to verify this. And you see that here you have first order with time, and here you have first order with space derivatives. Yeah, so you'll see that it's not always easy to take these derivatives, but that's a different story.
And also the Lambertian, from what I remember from my particle physics course, there is no 2, just a square.
Just a square.
Just maybe it's
The square is not square.
Really? I don't remember. I like to put a square, but check it.
Isn't it just the operator of the wave equation?
Yeah, it's the operator of the wave equation. This is what I mentioned here.
Yeah, so why are we giving it a different name?
Because it's shorter.
Okay.
Look how short it is.
Okay.
That's all. And you want to give credit to the great French nation. Check this. Can you check this?
Yeah.
I remember the square, but maybe
Yeah.
not. It makes sense to me because the Laplacian is a triangle square, right?
Mm-hmm.
So And if I take the square root here, that will be, but maybe I'm wrong, maybe I don't remember.
No.
No 2. Okay, but I'm going to leave it. Okay, no 2. Where did you check this?
Google.
Google, okay. Thank you. I think it's stupid. Because of symmetry with the triangle, but okay. I'm not going to, I guess these are mathematicians, this is mathematical faults. Okay, so let us see, okay, let us see what's the time. Okay, let's take a 10 minutes break and then we will solve these equations and march on to the great victory. Okay, so, yeah, so the end of the semester is approaching. First of all, the last lesson, which is on June 30th, it will be not existing. If you recall, I already gave you back 2 hours in the middle of the semester, and the reason is I'm not going to be in Israel. If the flights are available. That's one thing. Secondly, that means I'm more or less soon starting to prepare the exam. The exam will be 4 questions. The exam, you will have to answer 3 questions. In this exam, you will have a sheet of basic formulas. Now, this basic formula sheet was created in previous years. You can find it on the internet. You can use that one. Just give it to me and say, this is what we want. If you want, you can add some more equations if you like. There are some in these formula sheets. I think it's already 10-page long. It's not only about things from this course, but there are some simple integrals, some simple identities that help you solve things. So maybe it's even bigger than 10 pages. I don't mind it, as long as you don't put in solutions to, let's say, previous exams, exercises, you don't put a whole Griffiths book inside. So everything is welcomed, and you can work on this. Okay, so let me briefly, I didn't explain yet the Lorentz gauge, and let me do that very quickly, hopefully. So the idea is, okay, the gauge. So as you know, let's say in electrostatics, a potential, I can add a constant. Now the question is, what do we add here? It's not going to be a constant, I mentioned it, but what is it and how do we add it exactly such that the fields are not changed? So, do you see this is good? I think it's okay. What's going on? So yeah, if I have A prime, which is a function of r and t, which is equal to sum A plus del lambda. Lambda is a scalar, which in principle depends on r and t. And then I have a potential V prime equal V minus d dt lambda r and t. The claim is that the fields E and B are equal to E prime and B prime. So what do I mean by that? Let's assume that we solve this equation that we have now, the D'Alembert and all these sources. Let's say A is a good solution and V is a good solution. Then A prime and V prime are also good solutions in the sense that they give the same fields. So what is the difference that we had from high school? In high school, all this junk was simply a constant. Now this constant is not a constant, it's a function. And here you have the del, and here you have the d over the t. So how do I know this? I think for B it's very simple, because what do I need to do? I need to take the rotor of A prime, That's B prime. Rotor of A prime, rotor of this junk, and this will give you 0. So it's trivial that B is equal B prime. By definition, the definition is by this, where once I put B prime is with A prime and B with A. With V, it's as easy in some sense. All we need to do is use this definition for E. So what is E prime? Let us do that a bit more slowly. It is minus, by definition, B prime d dt A prime. This is just this definition that I put in here. But what is this? This is del V minus, which will turn into plus, del d dt, the function lambda, minus d dt A, here this one, taking d dt A, minus d dt del lambda. You see these two guys simply cancel, and what do I have here? Div V, the potential, the previous potential, and minus d dt. That is exactly simply E. So we see that with this transformation, E prime is equal E, and that's why you are always allowed to take this direct transformation. Now you can ask a different question. What is lambda? So what do you need to do? Let's say if you know what to do to find lambda. Let's just say that we know A and we know V. Now we want to find the lambda that satisfies the correct equation. So what will happen, you just need to plug this into the equations that we had before with the D'Alembertian. You will have a connection between this lambda and this A that brings you to this A prime and this V prime. I can write it for you. Are you interested? You want to see this? Okay, so so let us see, and in particular, let us see how this one. What does this mean? So now let's be. What I did now on the blackboard was a general transformation. Now let us be specific for the Lorentz. So what do we claim in the Lorentz? We say that div A prime plus, I'm just copying from up there, and I'm taking this and putting it on the other side. U0 epsilon 0 d dt V prime is equal 0. But this is what is it equal to. Now I'm going to plug into this one and this one. I'm going to plug A and the function lambda. That's all. So, which are general solutions. So this 0 is also equal div A plus U0 epsilon 0 dv dt. So what am I doing here? Remember, A is proportional. A prime is A plus some derivative of lambda. So you see here I just use the first term, and here I use the first term, and now there are correction terms. And these correction terms are lambda minus U0 epsilon 0 dt squared lambda. So if we call to all this function f, it's some function for the first field, A and V, then what we have here, as Ofek taught me, this D'Alembertian is equal to on lambda is equal minus f. Now, why did I not derive this? Because we don't care about this so much. Why don't we care? We care about only one thing. For some A original potentials, original A and original V, there is some F, and then for this sum F, there is a solution to this equation. So all we care about is that there exists a solution. And it's reasonable to assume, and mathematicians prove that there is a solution to these type of equations. And it's not surprising for you, because this is exactly what we had before. I mean, with the source, which is this F, which again depends on A. Let's write it down here. This depends on the originals A and V, and through them on R and T. So there is some solution, and then there is some lambda, and then we are done, because we choose them. If you find for A and V this lambda, then you can have this A prime and V prime, and now we can forget about lambda for good. Is this clear, more or less?
We need to know how to solve this equation in order to get the lambda?
Not really. We just need to know that the solution exists. And we believe mathematicians, and we believe it exists. We don't need it anymore.
But
in a practical sense, we don't need to solve this equation. It doesn't mean that we don't need to solve the same equation that we had before with rho and A, with J, but not with this F that depends on A and V. We don't care about it anymore. That's the whole trick of Lorentz. This is why this gauge transformation is so beautiful, because it simplifies the equation. You get rid of this. There are many different A's that you can think about. We specify the gauge, and once we agree what is the gauge, then the equations here are much easier, and we don't care about what is lambda. There are infinite number of lambdas. You see the transformation. Give me any lambda, any function of R or T, it will work, right? So the number of transformations you have is infinite. But we specify a specific gauge, which is convenient in order for our equations to be very elegant and relatively simple. But let me promise you they are not so simple. And now we're going to solve them, or partially solve them, and see what do the equations mean. Okay? So if there are no questions, we can continue. So now we can solve these equations. And I like this one. Yeah. Okay, so what are we going to say? So let me remind you again. We have some material. There's no magnetization, by the way. There's no polarization here. We are working in just with J. And inside this material, there is some small box that we denote by d tau as usual, dx, dy, dz. This is the size of this box. In addition, we have some origin as usual. Origin, we can put it anywhere, and then there is, from this origin, we have this R prime. The contribution to the potentials A and V comes from a sum over all these boxes that are inside these materials. Inside this box, it's the same picture. There is some J, and there is some rho, something that you are supposed to give me in order for me to solve this problem. In addition, we have, as usual, the location of the observer, R. Some guy that is at this point, and at this point I want to calculate the potentials, and if I know these potentials, then I can calculate the electric fields. So, what are these solutions? The solutions are given, this is the potential. So these are at position R, this is a vector, at time t, and t is the laboratory time, the time that we are right now in. Here there's no fuss. Then we have 4 pi epsilon 0 as usual. Integral over the volume, and I mean the volume of the body. So there's a lot of elements inside, Let's assume this is a connected body, so this element, that element, we need to add them up, right? R minus R prime. So R prime is the coordinate that we are integrating over. So this is R prime, then you move here, 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 nearly as usual. You know why this is to the power 1. This is like the usual potential, right? The potential of an electrostatic source. This is PR prime T d tau. This is the solution, but there is a big change, and this T is Tm. This is what I called before the retarded time, and here is all the physics. But this equation from physical point of view is very simple. Why is it simple? Except for the Tm that we need to discuss. It depends on some historic time. And this historic time is not trivial because this historic time depends on R and R prime. So it's complicated. I'm not saying this is trivial. It's the opposite of trivial. Maybe one of the most non-trivial things that you'll learn in physics. But this equation, if you say, okay, there is some previous time, this is simply the usual Coulomb's law, right? There's nothing new. So this is like what we studied in statics. The same formula we had there, but then we had no time. Now, if you just replace time t, Tm with t, it's an approximation which is, sometimes it works not bad for small speeds in many cases, but Tm will depend on several things. So this is like, it appears like Coulomb's law, but in retarded time.
Can't we just translate the retarded time into starting conditions, and then it becomes the regular Coulomb's law, but still has some time dependency?
I don't know what you are talking about, but the answer is no, even though I don't understand the question. It's not simple, but what I heard about, you can go into usual Coulomb's law. In usual Coulomb's law, there's no speed of light. There's no c. This one, the solution does depend on c. And again, the meat is in this Tn. And what is the vector? And secondly, this V by itself, if you want to calculate the electric field, is not enough because we need also the A here. So what is A? I'll write it on top here. So A is a vector, again, at r and time t. And maybe now not less surprising, it's exactly the same as before over the volume d tau and r minus r prime j r tm. That's it. Which is again like what we studied in statics. Now, here I want to remark several things. First of all, here we have the Tm. That's the most important thing. In Griffiths, this is called TR. R for retarded. Doesn't mean that they're stupid, it just means retarded. This is M, this is, sorry, but this is a word in Hebrew, mefagel. So this is the, I use M and not R because R is also the position, so I feel it's better to use M. But usually people write it with R. Secondly, this equation look very, very elegant, but it's highly non-trivial because you can say the following. I have here this backward time that more or less you have some feeling to it, and soon we'll define it. why don't I do the substitution not in V and A? I do the substitution in E and B. If you do it there, it will not work. It works only for A and V, and from them you need to get E and B. So this simple substitution and simple Coulomb law and Biot-Savart law remains, but only for the potentials and not for the electric fields. Okay? So it depends what is your choice. Now, how do I know this is correct? I'm not going to do it right now. We'll have other mathematics. This is in Griffith. You just need to use the equations that we had before with the Delaunay-Teretian, and you operate on them and you get these solutions. Okay, and of course, this is the this is the beginning. But what is this Tm? This Tm is the retarded time. Is the following thing. And here comes the complication. So, again, let us plot what we have here. We have this delta tau, which again we sum later, and we have this is the origin, this is r prime, and here we have this p r prime t and j r prime t. This t now, I'm not saying t when you observe, but the whole history of time. This is something that is moving. And then from this, I'm going to write it, plot it again. Now we are going to the observer. So this is what we called, so this is, so this is the origin, and then this was R. The R, again, this is the origin. So here is my reference frame if you want. This is the origin, this is the distance R, and this was R prime. So what is this distance?
R minus R prime.
And I'm going to just write the absolute value here. So this vector from this element depends both on R and R prime, and it's trivial, and it was like that all along the course, and it also appears, for example, here. You see this in this equation. So what is this retarded time? So first of all, we are using here an effect called causality. And that is the past can influence the present. This will become clear soon. It's a trivial statement, but the statement is that the future doesn't influence the present. So we have some propagation, and soon you'll see that actually this is what I mentioned briefly before. There are two times. One of them is that this Tm, and then there is another time called Ta, T advanced, and both of them are mathematical solutions of the equation, but we throw away one of the equations because that would correspond to something in the future going back in time. So if you want to phrase this kind of in a strict way, we have Maxwell's equations. They have some solutions. Some of them come backward in time, some will come from the past forward. And we throw away some equations, some solutions that come from backward in time. What does it mean? That Maxwell equations by themselves are fine, but in addition we have to use common sense or add this principle to the Maxwell equations in order to get the physical equations. So as a strict mathematician you would say Maxwell equations are not enough. You need Maxwell equations and causality together So this is a principle that you add to the equation. But for physicists, this is a kind of trivial, it's obviously because we're all getting old and soon you're going to finish your bachelor degrees. And so we find it natural, but it's stated. And the other thing is, of course, that physical phenomena does not propagate at speeds faster than the speed of light. And going backward in time means much, much faster than the speed of light in some sense. Okay, so what is this Tm? It's very simple. T minus Tm, I mean, it's simple to write, but it's not physically so simple, is simply this distance divided by c. So what does this equation say? The present time minus the retarded time is the distance from the element to the observer divided by c. So the way you can think about it is the following. This element is changing in time, the density and the current, but what is important is the time where, once you meet an information, let's call it, at the speed of light, will reach this point exactly at the time t that you are located at, right? This, I think you all see this from here.
Can you explain it again?
I'm saying that what affects you here at time t. First of all, we are going to talk about what affects you at this moment of time t from here. So it's a specific location. We assume that, or we don't assume, the equations show us that this information that was created in this time, t minus tm, which traveled in the speed of light, exactly reached this point at time t. And this is a definition of this tm. Okay? Is this clear? I mean, it's a statement, it's not a proof. Is it clear or not?
Can you repeat it?
At third time.
Yes.
But 2 times didn't help, so. I'm saying, imagine, okay, I'll say it differently. Imagine that you turn on a pulse of light at some previous time t, which we call Tm. And this pulse of light will reach this point exactly at time t. This pulse of light has to be created at time Tm before t. That's why it's called mefagel, retarded. And it travels this distance, so it reached after this time. So this is the distance divided by the speed, which is c. And that's it. This is this Tm. So Tm is t minus r prime over c. Now, you need to plug it in here. And then you see the mess. You see a big mess. Because this d tau, this Tm depends on, as you see here, it depends on r, it depends on r prime, and it depends on t. It also depends on c, but that is a fixed thing. So when I do the integration over the space, usually we think, okay, here we have an r prime, here we have an r prime, but now also in the time we have an r prime. And where is the r? The r is in Tm and here, in 2 places. Why is this important? When I will take the derivative of this, let's say with respect to r to get the, let's say the part of the electric field, then the derivatives will be with respect to the r which is in here and with respect to the r that is in here. If it would be only with respect to what is downstairs, this will be like electric field that is given by the usual Coulomb, because this, you get here the famous 2, but now there's something inside. So the electric fields are going to be a bit of a mess, Maybe I'll write them later, or maybe I'm going to write them now. Yeah, okay. So let us summarize this part. So the summary now is we have, in principle, V and A, from which we can get E and B. We use the Lorentz gauge. The retarded time Tm depends on R prime R and T. I mentioned briefly there is another solution, again, solution of this equations for A and V, where we have T advanced, which is given by T plus R minus R prime C. So these, you can put it in here, TA. You can check that this is a solution. But this we ignore because this is the advanced time, and this we ignore. I'll discuss a little bit more on this advanced time a bit later. Of course, how did we get the speed of sound? Eventually U0 epsilon sound of light is c squared. And etc. Okay, so now let us solve one example, relatively simple example, that is given in Griffiths also. So maybe I'll leave this. So Griffiths wants us to solve the following equation, following problem. We have a tube, and this is going to be the z direction, and I have in it a current. This is a wire, so it's a one-dimensional object. We don't have J, we'll have I. And this I is switched on at time 0. So the current is switched on at time t equals 0. So I of t is going to be a constant for t greater than 0 and 0 t less than 0. So it's a step function. How is the step function called, do you know?
Heaviside function.
Heaviside. You know what Heaviside did in life? Not this function. Electricity. He solved all this. What I'm talking about is essentially the work of, a lot of it is a Heaviside. Not only, but it wasn't Maxwell who solved his equation, it was Heaviside, and he invented this, and eventually only this is, many people only remember this. So this is a Heaviside function, and then the question is, of course, what is E? And what is B? So here it's like the switching on problem. So at the beginning we have no current. What do I mean by beginning? Before time 0 there's no current, which means no magnetic field. There's no charges here. So there's no E and no B, and then you suddenly switch it on, which is an idealization which creates problems, but we'll assume this. And then you get what? You get, what do you expect? So after a very long time, what do you expect in vicinity? Long time and not very long distances. So what do I mean by long time and not in short distances? That, you know, you turn it off, you turn it on, and you are 1 centimeter away, and then you are looking at it after 1 year. So the light already went to plus infinity, you don't care about it. So what will happen here at very long time limit is you have here an I, and then what we'll have? Magnetic field that you learned in high school with the right hand notation in the phi direction, right? Like this, because it's flowing this way. So, and what will be the electric field? According to high school, it's actually going to be 0. There is a subtle point here. I'm not assuming any Ohm's law and anything else. So there's no dissipation. So we're not losing energy, because what is physically happening here is that the electromagnetic field is carrying energy pointing vector to infinity, but nothing is lost. We are conserving energy here, which means that the electrons inside here that you create are not colliding with anything inside. So this is a very idealized model. Again, no Ohm's law, no approximation, and no dissipation. Okay, so I think this is the problem, and this is rather clear. So let us see what will happen, and I'll. Okay, so what will happen? So we are going to define, this is the z-axis, and we can have some z equals 0, and this is going to go call s. So s is some distance from the wire, and you have a cylinder, if you want, along this wire. This is distance s, and from symmetry, doesn't matter where you are on this cylinder, as long as you are distance s, it's all symmetric. So we have this distance s. So here is where your observer is. And this is z is where the current is. Okay, so now what will happen, just physically? So let's say that Ct is smaller than s. Then remember, we turned on the field, right? We turned it on time t equals 0. So if Ct is less than s, what will happen? Nothing. You will not know about this turning on because the information didn't pass. So if you want to think about it like this, here is my current I, and then this is Ct, and this is s, and far away. So this is the horizon of information, if you want. What is the information? I mean by information, the basic fact that you turned on the current, and then you expect nothing. Now, this is, I did it here for the element. I mean, there is an element I, but there are many elements. I mean, this is just below the point I'm looking at. There are also elements here, 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 and etc., etc. So what will happen is that there is a kind of triangle with Z min and Z max, beyond which, so there are more points here and more points here, but these points cannot transmit information in such a way that at time t will reach the observer at this point. So what is this distance? This is Ct, this is Ct. So if you are here, the information arriving here did not yet arrive, right? I think this is clear. So we have this, I call it triangle of influence, but more correctly, it just means that the I inside this part is important and everything else is not important for us. Now we can say, what is this Z min and Z max? What is Z max, for example? This is simple Pythagoras. Z max is equal to Ct minus s squared, square root. And Z min is, of course, minus Z max. Okay, here I mean with the plus solution. So we have this solution. Now, what do we need to calculate? Okay, we have two equations. One of them is A, and one of them is V. We want to calculate, let's say, the electric field. Which one do we use?
We need both.
Both. But this one, in this case, is trivial because there's no charge density. There's only J. So in this case, because rho is equal to 0, there's no free charges. we have only j, and we're going to use only the equation for a, which is a bit strange, but we already talked about this. There is only a, but a, because it depends on time t, will give you some electric field, and of course, as usual, I would say, it will also give you a magnetic field. So it will give you both. So in this particular cooked-up pedagogical example, we just need to calculate a, which is a good thing. So if you think about it, okay, so the j, what is the j? Here is a three-dimensional integral, but we did these transformations before. Transformations, I mean, from a current density going to a line density. What you need to do is you replace the integral with d tau, with what? With integral over dz, like before. And you replace the j, you replace with an I. So instead of d tau j, we have I dz. Remember, if it would be in two-dimensional, we'll have k dx dy. Remember these transformations. You can do it rigorously, but we did it already, where you replace this j with some delta functions, and then this integral over the trivial delta functions in this way, and in the x and the y direction becomes 0. So using this technique that, okay, this was the first part of the course, we can easily now write down at least the solution, and hopefully this will just be a good thing for you to start thinking about this problem. And then what we are going to do is, I'm going to use this a, is going to be, it's essentially a function of s and t from symmetry. There's no, so first of all, what is the direction of a? Let's write it from the beginning. The direction of a is direction z. Why? Because the current is in the z direction. We're going in the z direction. This is the z direction. So we know the direction of the current, at least that. You always have u0 over 4 pi. Now I'm going to write here 2, an integral. I'll soon explain this 2 up to z max. Okay, and z max, we have it before, ct squared minus s squared square root. And now we have I0, which is a constant. That's the good thing about a step function. If it would be not a step function, it would be much more complicated. You immediately understand the integration is much more complicated, because what happened here essentially, if this is a constant, then the influence of Tm just comes on the boundary condition. So this is the simplest thing that you can imagine. And then we have here z squared plus s squared square root. Now why do we have 2? Because the integral is actually from minus z max, but then you do it 2 times. And here I have dz. And yeah, this, what is this z plus z squared? So I mentioned there is this triangle zone, right? But if I'm here, this is s, this is z, then this is z squared plus s squared square root. So I'm going dz, 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 and from here this is the distance, so this is the distance which enters, replaces this one here. And eventually the largest one is given by this one, and eventually the largest one is cut off by this horizon. Okay, this is the best I tried to explain. And then, okay, this is a trivial integral because we expressed everything. You do the integral over z. S is a parameter, again, it's just the distance. And then we get this very nice and simple equation, A equal st is in the z direction, u0, I, 0, 2 pi, the natural logarithm of ct plus ct squared minus s squared, which comes from the max divided by s. And the condition is that ct is bigger than s. Maybe this is the most important. Otherwise, it's simply 0. So this just means that what I said before, that in order for a solution to exist at all, you need that S to be inside the zone of the information that is C times T. And again, T is with respect to the turning on of the current. Okay, so now I have A, and now it's relatively easy to find E and B. So I'm not going to go into the simple math, but it's a simple exercise to find E and B. So first of all, what is the E? Well, the E, in which direction does it go? It goes, you see it from here. Again, there's no V, so you just need to take the time derivative of A, so the direction of E is the Z direction. So you have the current in the Z direction, and the E is going in this direction. Okay? Now, this is not super surprising, because from high school you know the direction of B. So you're kind of, based on what we had in this course, we kind of expect that E and B should be perpendicular, and you know that B is with the right hand going to come out. So this thing is true, and also why E and B should be, if E and B are perpendicular, that means that there is a flow of energy going out. So if I turn on this thing, there will be a vector pointing that will send some information or some electromagnetic fields out in space, and this will carry energy flux, which is what you do when you use your phone, more or less. So what is the E? Let us write it explicitly. E is minus dA dt. So it is parallel to Z, because A is parallel to Z. And this E is given by this nice equation, minus U0, I0, 2 pi, then there is a C, because you see when in such expression, when you take the time derivative, you get out a C, because it's always CT, and here you have divided by square root of CT squared minus A squared in the Z direction. And this is, or it's 0. And this is for S less than CT. This is for S bigger than CT. Now, this solution has some peculiar, interesting things. What do you see from this solution? It decays in time, because there's both time and space. So, decays in what? So you see, but yeah, you're correct. Long time. And what do I mean by long time? That S is fixed. X is some distance, and you're not changing it. Long time, then this decays, and you see how it decays. E is proportional to 1 over t. It goes to 0. Eventually, it will go to 0. And this is exactly what you expect from high school, because in high school, the speed of the velocity is kind of infinite. So sorry, maybe not. No, you don't learn this in high school. I'm sorry, because you don't learn it when you switch it on. Long time is the same as a current that is constant, not turned on, just a constant current, right? And this is exactly what you learn, that the electric field doesn't exist. It's true, but somewhere when you turn it on, it does exist, and eventually it dies away. So everything that you were taught previously is correct, but it's a long time limit, if you want, not a short time limit. This is fine. But another thing that you see here is that when S is proportional to Ct, slightly less, this blows up. This electric field goes to infinity. And this is a bit strange, that electric field is very strong, because you see, as S is approaching Ct, this is 1 over 0, this is very big. E goes to infinity. Now, this should bother you. How can this be? I mean, if E goes to infinity, then I can switch on a field, and then it will arrive at you, and the electric field will be infinity, and then all your molecules will be broken, and all your electrons will be thrown away. I cannot really do it, and the reason is this happened. Why? Because I turned on the field from 0 to something at epsilon time, at no time. So if you have a real pulse that goes up slowly, it will not diverge like this. So this divergence is due to the idealization of the pulse. It's not you can never reach it, but the more the faster you change, the pulse will go up like that. Then, yeah, you will produce bigger and bigger electric fields. You'll never reach infinity, but you can reach high in principle. But of course, that will cost you energy. It's not so simple to take. What does it mean? What does it mean actually? We have no current, and then the current is something like that. What does it mean? It means that we somehow accelerated the electrons from 0 to some speed at finite 0 epsilon time. This is impossible, of course. And okay, first of all, we'll have a smoothing, and secondly, it will cost you energy to do this. But then if you're able, we can turn on this pulse and kill all the Iranians far away in principle. But theoretical physics is not, I mean, I just do theory, so in practice it doesn't work. So this is the electric field. And then the magnetic field is, what do I need to do? I have this A that I'm now wiping out. I need to take the rotor, and again, that's also easy in principle. Now it's easy for this problem. And then I get this B, which is B is equal to U0 I0 over 2 pi S CT square root Ct squared minus S squared phi. Phi is the right-hand angle along the wire. Now, you are familiar with this part of the equation, and this is the new part of the equation where you see the time dependence. So what do we see here? When t goes to infinity, again, I mean S fixed. Again, this by the way, same condition, S less than Ct, otherwise it's 0. So what do we have here? This goes to infinity, so this is Ct, this is Ct squared, but it's much bigger than S. So all this goes to 1, and then B is U0 I 0 2 pi S phi, like the well-known equation for an infinite wire. So B doesn't, unlike E that goes to 0, B doesn't go to 0, which is what we expect. You also see that B diverges, B like E, diverges when S goes to Ct from below, which means that the vector pointing is going to be tremendously large exactly at the front. Okay, so let us go. One second. Yeah, let us go now to I want to write down an awful equation just to leave it Yeah.
Will I get the same result if I plug in TM for the web server?
The what?
Web server? If I calculate the D from the web server, but substitute TM. Will I get
Substitute what?
TM?
TM. Yeah. This is this. Yeah, of course. This is what I did now.
No, not from A. From
In the B itself.
yes.
This is exactly my point, and the answer is no. And I want to emphasize this point. So I'm going to write now, it's not for you to be upset or anything. It's just for you just to discuss. So this approach that I have here, we calculate A and we calculate V and we have very nice equations. But then you can ask the question, I think this is your question, why don't we write equations in general for E and B? You asked it for the example, but now I'm answering it in general. Okay? Why don't we write down the solution for E and B and let's forget about B and R and T. So I'm going to do that in general, and you'll see how complicated it is. But we will see some simple things inside. And after I show you these equations, then you will say, okay, let's use A and V. And the substitution has to be only here. And, okay, so this is a guy called Jeffimenko. I guess you never heard about him. And this is amazingly at 1966. Okay, for you 1966 is like prehistory, not for me. So it's relatively late. I mean, all this was done in before the 19th century. But and there was a reason why it was only then, and there is a reason why we should look at it. So if I use these two equations and I want to calculate E in general, what will I see? I'll write it down, but you don't have to. You have the integral d tau. Remember, I have some volume with the rho and the density. Rho, which is not as surprising, r prime, Tm. Here I have r minus r prime to what power? You can guess. 2. R minus r prime hat. This is what you said. This is just replace with Tm. You see, this is the electric field of a Coulomb where you replace T with Tm. The problem are the next terms. Plus rho dot, the derivative of time of the rho, r prime vector of Tn, C r minus r prime. So this is already non-trivial term. First of all, you see, if the speed of light would be infinity, this would go away. And we will be left only with this, and then it will be much simpler and nicer. But then there is another term, minus j r prime Tm c squared. Sorry, there is a dot here, the time dependent, r minus r prime. That's it. So this is the general, most general solution for E. And you see that it is not so elegant because there are 3 parts in it. Now let us ask simple questions. Why do we have 3? Where do they come from? So can you say why do we have 3 parts now? So first of all, the good news, yeah, everywhere we have this Tm, Tm, Tm. Now we have rho dot and j dot. Where does this term come from, j dot?
What is the vector of the second term?
It comes from the
Yeah.
from the J.
Sorry. Thank you. Very important, there is a vector. It doesn't matter because you're not going to use it. Because you see it's complicated. Yeah, but where does, let's talk about this J dot. Where does it come from? Why do we have a term J dot?
Come from the three, maybe from three component of J that we had when we talked about electromagnetic
Yeah, maybe,
material.
but no, there's a simpler answer that I'm looking for. Why do we have a J dot? What? From the ADT, someone said that, I don't know who, but someone said it. So the electric field depends on the time derivative of the vector potential A. And if I take the time derivative of the vector potential A, where do I have time here inside? It's hidden inside the Tm, because Tm depends also on time. So I'll have to take the time derivative, then the internal derivative, that will give you all this C, etc. And you see the time derivative is here, so what you have down here is remained as is. And you get outside this C somehow. So this comes from dA dt. From the basic definition of the electric field that contains the vector potential A. Where does this term come from? So this term, where does it come from? Well, it doesn't depend on J, so it has to come from this potential, right? But why do we have this term? How do we get from V? We have the derivative of time of A, and what do we need to apply on V? The del operator?
Yeah.
So when we apply this one, then we look carefully, where do we have R? We have R here, and we have R here. So when we apply it here, so first, when we apply it down here, okay, we get this one. This is well known, because this just gives you the grad of R minus R prime. This gives you the famous Coulomb's law that we have here. But when we apply it here, we have the R inside, so it's over the time, so that's why you replace the derivative with time, and then you have the Jacobian, and then you get this rho dot term. So this comes from
The chain rule of the
rho.
space derivative.
The derivatives in time at respect to
The derivatives, when you calculate the fields, wait. Again, Tm is a function of R, R prime, and T.
the level.
Yeah, so when you take the time derivative, you take it with respect to T, not with respect to Tm. When you take the special derivative, you take it with respect to R. Because why? Because you are calculating the field E and B at a specific point at a specific time T, laboratory time. Okay, I'm not doing these derivatives, but this is obviously here at this, I emphasize the dependence on TR, and that's why you have all these three terms. Now, when you look at these terms, what is interesting about these terms? So, okay, these are the new terms, but you notice something very important, actually. You see that this guy decays like, I'm going to emphasize, this is to the power 1, this is to the power 1, this is to the power 2. So imagine that your density, rho, and the current density, J, they are all localized in some region in space, which has some dimensions, call it A, some sphere, whatever, doesn't matter. Which one, for large distances, what will win? This one. So this guy win at very large R. Eventually they become more important. So we all understand, I think, that if C, of course, if C goes to infinity, they vanish. They're not there. So it's a matter of taking the limits. So some people ask me, these are the non-expected terms, right? For small velocities, can we throw them away?
No. For small
Yes and no.
velocities of the particle or of the light?
Of the particles, let's say, of the particles. So it depends where you look, because at large, you cannot neglect this compared to this at large distance. So you can say, okay, but at large distances, also this one is small. It's correct. This one is small because it has to decay like 1 over R. This one decays like 1 over r squared. But if you are looking at a signal far away, you care about the other terms. And these are the signals that actually propagate in all electromagnetic radiation, transformation, everything on the modern world is based on these terms. Not only that, they decay like 1 over r. This will be super important. Why? Let's assume also b decays like 1 over r, not like 1 over r squared. What is E times b then?
1 over r squared.
1 over r squared. Now, what is E times b? This is the Poynting vector. It goes like 1 over r squared. Now you want to calculate the energy of the whole thing. You need to integrate over r squared dr. Why? Because that is 3 dimensions. 1 over r squared times r squared is a constant. And that means you can transmit information in vacuum at least forever. And that's the modern world, because this is what you're doing in communication. You can transmit for long range because it decays so slowly, 1 over r, not like 1 over r squared. Because with 1 over r squared, this argument doesn't work. Because if E is 1 over r squared and b is 1 over r squared, Poynting vector is 1 over r to the 4, and then the integration over 1 over r2 will vanish. This is super important. So you will see in radiation that these terms are super important, and then I disagree that because in modern life you cannot say that, you know, small velocities, they're not important because it depends on how far you are looking at these things. Not only depends where. But again, if you are not too far, if you don't care about things that happen far away, then okay, you can throw away everything and you go back to the usual approximation, which is more or less this one. Okay, so I'm not going to write B. Okay, so let us now try and use these equations now let us consider a point particle. With charge q. So for a point particle, we have, first of all, we're going to define the path. It's not with a constant speed, there's some path. Your particle moves here, from my point of view, it can be a crazy way. And you have here some path, omega t. T can go from minus infinity to time t of the laboratory. This is your path. It moves. If you want to think about a straight line, fine. If you want to think about the spiral, also fine. So this is the trajectory of the particle. Okay? This is my definition. Is it clear what is this W? Okay, so now we are at time t. You are at present location. And there is some W at some retarded time. And this location, WTM, is going to be important. This is the position of the particle, the point particle, that influences some point over here where we measure the electromagnetic field. So we care about where you are now, but we care where you are in the previous history, but we have all the trajectory, we know it. I fix it. Some guy is moving it at this speed and with this trajectory or without acceleration. And this is what I'm going to denote by WTM. Okay, so this point is WT if you want. This is WTM. And now we want to calculate what is this WTM. It's related to what we already defined here. So with this trajectory, let us just copy this. We have some origin. So this is X, Y, Z. This is the reference frame. And this is our WTM. And this is our current location. Now, we also have an observation point, which is R. So here is my observer, for example. And then, as before, we have this distance, which I'm going to denote R minus WTM. So what am I doing now? In all this junk, we need to calculate Tm, but we also need to know what is WTM. There are two things to calculate. We need to know where it is in space and what is this time. So these are the two variables which are connected to one to another. And from the definition before also, R minus Tm, this is equal C T minus Tm. So what is happening here? I didn't specify the path, so you can have many different paths. But if you specify the path, the claim is that there is one position in space that will satisfy this equation, and actually two times. But one of them is going to be the advanced time, one is the retarded time, and we're going to throw away one of them. So this is just, what is this thing? This is this distance. So the particle was here in some previous time, and it submitted light over here. And this event, that the particle that was here, sent this information to this observer exactly at this R minus omega Tc. The distance is equal Ct minus this time. And of course, when I will change, for example, the position of the part of the observer, you will change Tm and you will change Wtm, etc., etc. This is pretty obvious. So, what is, we will focus only on V. What is the potential V? I write here potential because there's also velocity of the particles, so V potential. This is equal, well, first of all, it's not equal. This is again the question that was asked before. It's not equal, it's wrong, but it's good to make mistakes at the beginning. WTM. So, simplified, you solve this equation, you find WTM, and then you put it in here, and this would be Coulomb's law. This is wrong, but it's not sometimes it's not a bad approximation. And this is exactly the point. So there are two effects. One of them is this one, and another one is that this Q you need to replace by some Q effective to get the correct result, and I'm going to discuss this Q effective. So there are two effects going on. One of them is you kind of renormalize the charge, and the second one is that you need to look at the retarded position that influences you at time t here.
Q effective will depend on Tm.
Q effective, yeah, will depend on many things, but it's complicated. So, but this is just a way to think about things, and we will specify this a bit more soon. But let us write down the solution, and then I will derive it. So the only mathematics will be the derivation of this guy. That will take me, yeah, you will dislike it maybe, but whatever. I want to show you some math and not all the math. So I chose to show you this one. I should show you. So it's R minus omega Tm times C. So if I stop here, this is exactly the same like here. You see the C and the C vanish, but there is a correction term, minus, R hat. R hat is the unit vector in the direction of the observer. Sorry, it's not hat, it's R, minus omega Tm. Again, the same vector, but now it's a vector, dot Vtm.
Will
So-
be the speed of the particle.
Yes, but not, so VTM is the speed of the particle at the retarded time. Now, you can more or less see, because I can take this one outside and divide, this will give you the correction that will give you the Q effective, more or less. But what I want to point at this stage, that this is a very strange potential, because it depends on velocity. Usually you think about a charge, it creates a field, or a potential field, it's independent of its velocity. I mean, you know, if you use this in some kind of Newton's equation, then you get inside the velocity somehow. So this is very different than what you are used to up to now. And this is also very basic in some sense, because what am I talking about? The potential of a moving charge. Now this potential is called Leonard-Richard. There is a similar formula for vector potential A, which I don't write. And both of them are needed. Leonard was a French guy. This is something like 1898. Very long before, let's say, Jefremenko. This is very old. And very basic. And from here you can do all kinds of things. And it is for, it's for any path of a single particle with some trajectory. So it's a very basic equation indeed. And because it's basic, and because actually I think in Griffiths it doesn't prove this, I'm going to prove it now with some math. So if you don't like math, you can go away, or you can stay, depends on you. Let me prove this. What do I mean by prove? We will use the equations that we had before and derive this, and you will see, especially with this part, which is the non-intuitive part, comes from how do we get the velocities here? So intuitively, from the rho has to be what? It has to be a delta function. Inside T, we will have the definition of Tm, which is here. And then when we
Supposed to be a delta function of velocity, or
I'll soon write it down, but a delta function of r prime, but because it's a point charge. So you will soon see how do I get, because from here, how do I get velocity? I mean, maybe it's obvious and maybe it's not, but it is not. It actually comes from some Jacobian, as I will soon show. So this is not totally trivial. So let's do the math. And later, if we have time, we can explain the physics more or less. I guess I'll wipe this one. So what do I need to calculate? I want to calculate the potential. Okay, V, R, T. What do I need to do? What is the price? I just copy this equation essentially. Q over 4 pi epsilon 0. Here I identify this rho as Q times the delta function. So this is this Q, from this rho comes this Q. And this is this 4 pi epsilon delta. And then I need to integrate over the volume. What does it mean, the volume? Now it's actually overall space, because the delta function gives you contributions that are zero overall space, except for where the particle is. Okay, this is delta 3. 3 is for 3 dimensions. R prime minus the trajectory yeah. I'm going to write it immediately like this. r minus r prime d tau. So what did I write here? I hope you understand what is written here. So what is the charge? The charge is a delta function of r, but where? Where the particle is, but at time Tn. So this is the position of the particle. I used already this one here. And this is the position of particle at Tm, because this is what you need to use here. So what I did here is, yeah, Tm, you see, sorry, this was the general, okay, I'm going to prove this, but this was the general definition of Tm. If you remember, this was the general definition of Tm that we had before. This is not yet exactly what you have here. Okay, so now we need to integrate, and this is a mess. So what is the trick? Does anyone have an idea? What is the trick? That will be...
We're integrating over r prime, over delta
Yeah,
function
over
of
r prime, as usual. We are integrating over r prime, but
So why is this a mess?
because r prime appears here and here.
Ah,
And it's a function of r prime. This w is some general function. I think it's a mess. So,
Maybe you can use the definition of the delta function as sum of the zeros, one over sum of the zeros of
sum of the zeros. You can use many representations for the delta function in principle, but the trick here, it's not a trivial trick, is to add one delta function to make things simpler. So we are going to write this like this. We're going to write this as q 4 pi epsilon integral dt prime from minus infinity to infinity. So I'm adding an integration, integral d tau over the volume, 1 over the usual r minus r prime, delta function, this is a delta function of r minus omega t prime, delta function of t prime minus t, how do I want to write it, plus r minus r prime c. So what did I do here? Essentially nothing. I have here this new delta function. This is in 3 dimensions. This is a delta function in 1 dimension. And then I say this t prime is this t plus t, like here, minus r prime. So when I do the integration over d prime, this junk will go here and I'll go back to here. Everyone sees this? You see that if I do the integral over dt prime, here I have t r minus r prime, which is exactly the same. You just plug it in here and then you'll go to this if I do first the integration over dt prime. So what is the trick? The trick is...
integration over the space.
Yeah, exactly. So we're going to do the integration first over the space. And this is already a little step because we had, here it's a 3-dimensional integral. But now I can easily do this this is r prime, like this r prime. Now I can easily do this integral, and this is equal integral, I'm still left with the integral over time, t prime, which is just a dummy time. And yeah, so all I need to do, you see r prime minus w. So I need to replace in this delta function this r prime with w, that's all. And also downstairs, so I have here r minus w t prime, absolute value. Delta function of t prime minus t plus r minus w t prime. absolute value divided by speed of light. Okay? So now I have a one-dimensional integral, but it's still very not exactly nice, because you see I have here t prime and I have here t prime. So how do I do such integrals? The trick is like this. Let us define this guy, all what's inside here, as u. And now, after I change variables, I have here a delta function of u. What do I need to calculate to get this transformation? I need to calculate the Jacobian of the transformation. So this is u. I need to, because I'm going to do integration over du now, I need to find the derivative of u with respect to t prime. But this is relatively easy, but not so easy. So let us find this du dt prime. So let us write down what is u. U, it's a change of variables, t minus t prime plus r absolute value minus w the path, t prime absolute value to divided by c. This is a definition if you want. Remember, eventually I want to get this one. So if I delete this one, then stop it. I also wanted to get this one, but never mind. I deleted it already. That's very stupid. Okay, so I need to calculate the Jacobian, which means I need to calculate the u dt prime. So what is this derivative? I have here the derivative of this one gives you 1. The derivative of this guy, of t, with respect to what? With respect to t prime, is 0. And now I need to take the derivative of this guy. So let us write down what this is. Let us write it down here. So this is t prime minus t plus, what is this? This is x from the r. So x is the position of the particle at point r, the x component, minus omega x t prime squared plus y minus wy t prime squared plus z minus wz t prime squared, all this square root divided by c. So x, y, and z give you this vector r, and w has 3 components, wx, wy, and wz, and they are calculated with some previous term t prime. And this is by definition this thing. Now, unfortunately or not, I need to take the derivative of this. With respect to what? With respect to t prime. And you already see something nice. When I take the derivative here, what will I get? A velocity. You see the velocity coming out because you have the d dot. But let's take the derivative now. The derivative will be equal to, there's a minus. The minus comes from here. Believe me that this is true. And now I have, this is the square root. Okay, c, now I have this square root. X minus x c t prime squared plus y minus wy t prime plus z minus wz t prime squared. So I just took everything, put it downstairs, and now I need to take the derivatives. So from the square root I get a half, and then the internal derivatives will give me also a 2, and then they will give me also a minus from here. But then I have here x minus omega x t prime multiplied by x t prime. That's when I take the derivative, so I have the internal derivative plus y minus wy t prime wy t prime plus z minus wz t prime wz dot derivative with respect to time t. So we see here the three components of velocity of the path at this special time t prime. But if you look at this for a second, 1 is 1, minus c is c. What is this object that we have downstairs?
It's r minus omega t.
Right, this is r minus omega t prime, absolute value. And what do we have on top? We have r minus omega t prime dot w dot t prime. And you see here, this is units of space, this is units of space, this is velocity, this is velocity. Altogether, this is 1 like this, and then it misses out. Okay, so now I can plug it all into, let's call this one Aleph. After changing variables, I mean. So again, I repeat, all this, this gives you the Jacobian. Now we are nearly done because we can now use Aleph. We can calculate V, R, and T, Q over 4 pi epsilon. Integral now over du. What is the delta function of u, which is going to be a simple thing. Here we have 1 over r minus omega. I'll write it like this, omega t prime of u, because t prime is a function of u. This is simply this, what we have here. This is the delta function, it goes into this one. And all I'm left with is the Jacobian, which is 1 minus all this junk we have there, r omega t prime again of u, r omega or w t prime of u, absolute value, dot omega t prime of u divided by c. It's beautiful. Because now I can do the integral. Because the integral of a delta function is easy to do, I just need to plug in u equals 0. Which means I need to plug in u equals 0 here. And then what do I get? Again, eventually, if I plug in u equals 0, what is this t prime? That's the retarded time that I gave you before. This is how you get the retarded time. The new definition of the retarded time, not over the whole space, the one that we had a few lines ago. So I define Tm, which is simply T minus RWTM divided by C. And then after I do the integral, essentially I get this result, but I'm going to write it again. We get the V potential, Yeah, okay. We get this. Let's call this equation bet. Okay, I'm either happy or sad that I did all this. Why did I do all this? Because every step that we are today in the class that I did not show you is as difficult or maybe even more difficult than what I did now. So there was for example, the solution of the D'Alembert-AI. You need to plug in to see that they are correct. You then need to go from potentials to V. Every step is a few lines of algebra or many lines of algebra. So I decided to do one of them to teach you it, because I feel this one is productive because you have these two delta functions and this Jacobian, which is a kind of a trick. So I choose one to solve one, but the math is there always behind the screens. So now, just a minor note. You see again. I just want to repeat that this guy I can take outside, and then you'll have exactly this structure. So there's you can put this outside, and then you'll have this thing out here, and then you have this ratio. This ratio is like this ratio. Hopefully you can see this, and if not, you go over this at home and try to understand the math that we did here. Okay, so so we will stop here. The math was explained, but the physics was not explained. So, I mean, part of the physics was explained, but not all of it, especially what is the meaning of this Q, this transformation. And then, up till now, I didn't even solve the simplest problem. What is the simplest problem? That this W is a constant speed. This is general still. You can have your acceleration, you can have your whatever you want, you plug it in and you see what happens. So next lesson I'll try and explain to you what I mentioned before, what is Q effective. It's explained nicely in my opinion in Griffiths with some trains and some transformation and Doppler physics. And then we will use in this equation the constant speed case, and we will get the field of that. Simplest case, constant speed. And then we will go to radiation, which is chapter 11. Okay, thank you very much. Unless you have more questions, you can ask. If not, goodbye. And by the way, one more thing. I just calculated V. But to get E, this is not enough. You need also A. So I didn't even do the whole calculation here. So.
יש לי